Sanskar, can you hear me?
Yes, sir.
So you are from which part of this
Yes, sir.
country?
I am from Raipur, Chhattisgarh.
Raipur, Chhattisgarh.
Yes, sir.
Have you picked up any Bengali?
Sorry,
Have you picked up any Bengali words?
little, not much.
थोड़ा थोड़ा सीखा.
No, sir.
Okay, it is 3:15. So I upload the thing, and I request all of you, first of all, welcome to this formal class. I have a request to you. Please don't take notes. Please listen to me. And if you have any questions, you can ask in the conversation, or you can wait till I finish the topic. It is up to you. Okay. So with these few things, let me upload my PPT. Is it coming?
Yes, sir.
Can you see it?
Yes, sir. Yes.
Okay. So here we go. This is the problem, because every time I have to come out of that. Okay. I go to the presentation mode. Now you can see. And can you see my cursor?
Yes, sir.
Yes, sir.
Okay. Okay, fine. So the topic we'll be discussing during this course, the topics means the part I will take can be very broadly categorized into three themes. Broad means it is very broad themes. So one aspect would be some properties and guiding principles of moving waters. I didn't write flowing waters intentionally, because when we talk about flow of water, basically we consider a slope. But water can move, and move very furiously, even without a slope, or even against the slope. That you must have seen during the cyclones, tornadoes, tsunamis. So the principles I'll be discussing will be applicable to all kinds of flows. Of course, this is a big subject. This is called fluid dynamics, and it's not possible for me, neither I have the expertise to touch upon each and every properties of that. I will pick up a few things which I feel that would be of interest for our, important for our course. The second one will be the strength of materials, and the factors control the strength of materials. So I will be mainly dealing with the strength of materials, means the natural materials, rocks and minerals, but the science is the science, so you can apply it anywhere. Again, this is a big subject of material science. I will pick up few things to suit the course. And finally, the aerial photo and imagery and its use. And nowadays is practically all the subjects where you have to go out or plan something, you have to take help of the satellite imagery or drone imageries, and how do they work, and what information it can give. Again, few principles I'll be discussing. Now, these topics are not entirely different, they are all interlinked. But again, for the sake of discussion, I have to divide it. And the main goal is, I'm not a person who qualify to discuss all the principles. But my main aim will be to use these principles to understand how a good construction, which is man-made, of course. When I say construction, it is man-made, can be erected, or the nature forms some very stable structures. And then, using these principles, we'll try to understand the destruction of natural structures. Destruction of natural structures in general way is landslides, physical mass movement, impact of water on the land or the structures, and of course the man-made structures. And it can be dam, it can be piers of the bridge. Of course, I mean, I don't qualify to tell you, I mean, what are the designs or what should be the designs, but I will say a few words about the guiding principles. So with these things, if you really go for in the coming days or months or years, you will see that the teachers in Jadavpur University, this is true for any places in the world, that there are two basic approaches. That you first you teach these principles and then give the examples, natural examples or the man-made examples. And there is another view that you first put these things and then try to explain what are the guiding principles. I, being an old-fashioned person, I love to go to this part. In fact, if you see the history of science, actually science developed in this direction. The first, this was observation, and then people try to understand why does it happen or how could it happen. And that's why all the physical or most of the physical and chemical laws came into being. Of course, those who do modeling and computer simulation, they may have a different view. I respect the view very much, but well, I will follow this. So first I will show you these things, the features, and then I will try to discuss the science. In fact, on a lighter note, this has been my approach throughout my career. I learned it from my teachers or my colleagues with whom I worked in India and abroad, that this is one thing which really, give me the real confidence to go for the forward model. Many people would say that forward model means you do the modeling, or forward approach means you do the modeling and then go to nature or go to some other structures. But for me, the forward model is observation first and then the interpretation. You must have read, at least if you don't read, you must read this famous book, this Arthur Conan Doyle Scandal in Bohemia, and there you will find this quote. This is the philosophy of my teaching. That it is a capital mistake to theorize before one has data. Theorize means you can read the modeling before one has data. That is observation. Insensibly, one begins to twist facts to suit the theories. Actually, in many cases, this happens. Remember that most of the collapse of man-made structures because of this reverse model, according to my definition, that you do the science first and go there and apply to nature. The thing is to twist the fact to suit the theories instead of theories to suit the fact. So with these few things, let me take you to this very general picture, that is the hydrologic cycle. Well, you know that Earth is the only known planet in the whole universe where you have known H2O in liquid form, what we call water. Since we have water and we have a cycle, water is not stagnant in the longer scale, or even in the shorter scale. It is not stagnant, it cycles. This is a general data. I have given you the reference. In case you need it, you can have these things. You will get these things online. And this is the channel. And if you need, I can give you the data. But I request you just to listen to me. So all these units are given in 1,000 kilometer cube for stagnant water like ocean water and other things, and the moving part is actually in italics, and that is in 1,000 kilometer per year. So when we have this thing, land precipitation, this is a dynamic part. So this will be 113 into 1,000 cubic meter per year. This is the annual precipitation. So this is how these things are. You must have known this thing, may not be this data. This is not important. Don't have to remember these things. But this is how the cycle operates. And just for passing, just as a passing remark, you will see this picture from your childhood. Maybe you have drawn this figure as well, but most of the cases, cloud doesn't directly give rain. That's a different thing. I will not get into that. So remember that this hydrologic cycle is not just a water cycle. It actually controls the temperature of the earth. In fact, the Earth's average temperature is 15 degrees centigrade, plus minus 1 degrees. Average temperatures per year from pole to equator. And Earth has its mechanism to behave like a thermostat. So when some warming event happens, they unleash some process that actually nullifies this. Sometimes they are not 100% successful, but in the long term, in a significant stretch of time, they actually control the temperature to that. So this is also an energy cycle as well. And this cycle also explains why we have soil, why we have erosion, and why we have rivers and the motion and the problem with the construction that I will try to unfold within my limited capacity of knowledge. And you can also have a look at the MIT open courses and to get an idea about how the hydrologic cycle is linked to different energy cycle and mass movement. So I stop here for this slide, and let me take you to the observation first. Oh, before I have prepared the things. You possibly know or don't know that H2O is also a greenhouse gas, that it holds the temperature, I mean the heat, and releases to the earth. But its average residence time in the atmosphere is only 9 days. Maximum, it can be 3 days. That means if a one molecule of ocean water makes its way to the atmosphere through the process of evaporation, it can maximum stay up to 9 days. Within that, it has to be precipitated somewhere else. But for carbon dioxide, this is little problem. This is a little problem. It varies from a few years to a couple of 100 years. IPCC, they uh, say that it varies between 50 years and greater than 300 years. That means if you pollute the nature, it will take a long time to cleanse it. So don't do this. This is the message. And you know that the business consequence of it. But what the IPCC did, the way we actually calculate the residence time like water, they used a different equation so that the number becomes big. But anyway, I will not delve deep into this controversial topic. So let us first take to nature. These are the photos I showed you in my last informal interaction. Now, no photography today, only science. This is Narmada River flowing from this part is east and this part is west, just flowing to the west. And here you see the water is relatively tranquil, but when it meets these rocks, it becomes very, very messy, swirling motion. And you can see the sound, this tremendous sound. And in this part you apparently don't see any rock, but the rock is lying maybe 2-3 feet below. So whenever the water hits an obstacle, it becomes very angry, means the motion becomes swirling tide, and it tries to move it.
Turbulent.
Yeah, it is known as, I'm not using this term yet. I will come to this term a few slides after. Okay, so it becomes really chaotic movements. So fluid always flow from high pressure to low pressure. If you see that water molecules move in chaotic movements, that is, there is a pressure gradient. That is random pressure gradient. And that is the reason why you have these things. Now, if you go farther upstream, this picture I showed, here you see, and look at the width. You can see from the scale how wide the river is. Normally, I mean, India has very wide rivers, wide and long rivers. And here you see that it is just making a fall. Still, it is very wide, but it is not cutting. Next, this picture you also saw that it's making a big fall, and you see the water dynamics. Terrible. All possible direction, all these eddies here. They're all such place. I mean, nobody can even stand. Just washed away. Will be washed away. Now, obviously, when you look at this, and if you go downstream, then you have these things. This picture I also showed, and you see a quite a pictures of these things. Now, obviously, the question is that why suddenly uh, water becomes so quiet, and why it is cutting deep gorges. Today, I will not address the second part, but I will try to address the first part. That why rivers, when it meets some obstacle, becomes very furious, and swirling motion, foaming eddies, and sometimes vortices. Terrible. Why it is so? Because this is the main reason, one of the main reasons of collapse of structures that develop, that had to be developed on the rivers, on the river bed. So let's see. So this is quite means I have making an assumption that flow here doesn't have any bumpy nature, very major bumpy nature. So all this movement, what you see, is because of the pedals of the boat which is coming out, and there is no visible eddies. What we saw in the upstream. Fine. Now, if I take a cross section, hypothetical cross section along the river direction of flow, numerically, it will be like that. It is layer after layer, layer after layer, and there is no mixing of layer. Red means a little velocity is a little higher than this yellow, and but otherwise it's almost parallel, and there is no mixing because there is no areas here across. So this is what one should expect. But again, I have made this thing just for your understanding, because I really do not know if I would make the section what it would look like. But if I make this assumption, then possibly I can use this numerical computed diagram. And I think I'm not bad in assuming that, because you see, this is this dusk is setting in, and then what happens? All the boats are coming to the banks, and flow is in this direction, and the boat is moving down slow, but still the owner of this boat had to paddle, and that makes this assumption nearly valid that you really don't see very great speed. Otherwise, that this would flow like this, and you would see some furious water at the end of this pedal. So this you cannot see. So my assumption is not that bad. So fine. Now, if I take a hypothetical section in that, what you see is this. Just one more thing I possibly missed. Now, if you see the particle motion will be almost parallel to the flow direction. Unless and until there is any swirling motion like this, there won't be any mix up of the two layers or more layers, and the particle path will be nearly linear. But here, a drastic difference. You see all kinds of mixing, no layering. It is because of these eddies, formation of these eddies. And when you have the eddies, if a particle move only along this direction, it can only displace a substance like this is Newton's laws of motion in the direction of the force. Displacement will occur. Of course, there are thrust, but again, I will not like to get into those things. But here, you see, when you have the eddies, you see a lift. There is a lift factor that it will try to take the material upward. This you can feel. Suppose you are going for a long drive in an empty street. I do not know whether you have the experience, and you are moving like this. So the wind will flow in the reverse direction. No wonder. And if you just extend your hand, be very careful. Don't extend like this. You may get hurt by another car. So you look around, and then if you just hold your hand like this, because the direction of motion, you won't feel anything. But you make a little angle. Just make a little angle. You'll see your hand is going like this. Just going like this towards the direction of flow, wind flow, as well as a lift. So whenever there is a big motion and these eddies are forming, so the wind, what you see, the relative velocity is actually like this. And that's why you see a lift. That hand is displacing like this. So if this is the scenario, then the obvious question is, who decides? Which factor decide whether it will be quiet or whether it will be furious? Which parameters? So the physicists really scratched their heads for years. Eventually, a solution, well, I possibly missed. These are the two difference. This is the particle path. You see the velocity change. You can see. So basically, what happens? It is through a pipe, and reverse is not through a pipe. This upper part is air. But when fluid moves through a pipe, at this point, a thin layer will have no velocity because of the frictional force between the immediate layer and the wall of the pipe. Since it becomes stagnant, and you know the first law of thermodynamics, that the kinetic energy, if there is a gradient, the kinetic energy will be, transferred to those areas. So since this little layer came to a halt, the kinetic energy of the immediate layer will be lessened because it will transfer it to this layer and so on and so forth. Still, the effect disappears. So if you take a profile, then you will see that for a laminar flow, that is layers after layers, and the turbulent flow, that is the swirling type of motion, is completely different. Now you may say that why it is the same. Here also you see this velocity is zero because of this friction, but why it is so? One would expect that it moves in chaotic direction. No, it is because of the mixing. Since the mixing occurred, so the entire mass moved like this, and that's why in this font you will not see any variation in the velocity, what you see in the laminar flow. So these are basic physics, so I will not spend much time on this. Now if I put the velocity versus time curve for laminar flow, let's say I take a time interval, let's say 1 day. I can take it at any unit of time. I mean, not unit, any stretch of time. That's the one. So since it moves like this, then for every layer, the velocity will remain constant. That is, it will not change with time. Of course, it changes vertically, upward or downward. For every layer, the velocity will be the same for a typical flow. But for turbulent flow, you have a time integrated average velocity, but at a particular time, if you want to get the velocity, you see these bumps. And that's why some spot moves faster than the others. And you have these gyratory motions, all possible movement, chaotic movement of the water molecules. And depending on how off the velocity is coming, the flow is from the laminar flow, that guides what will be the amplitude of that. It's just like an electrocardiogram, just like this, and this amplitude will depend on the more off from the laminar flow, more chaos in the system, this peaks will be more. What I was discussing, that the scientists were scratching their head, that what determines these two things? And these gentlemen, usually the scientists, teachers, and many creative persons, they don't have any religion, they don't have any land, they don't have any gender. They are the properties of the world, but motherland is motherland. He was an Irish-born mathematician, worked in civil engineering department throughout his life. Osborne Reynolds. Osborne Reynolds gave the first explanation what determines whether a fluid will be turbulent or a quiet flow. And his observation is known as Reynolds number. Of course, he didn't write this part. He only talked about this part. This Reynolds number, this concept formally was introduced to science by another great person whom you know. This is Professor Stokes, the Stokes law, the inventor of Stokes law. But anyway, so what he saw, I forgot to mention one thing. Remember the year of publication, 1883. I am little interested in history of science, but for your work, this time is very, very, very important, I tell you. And I will come back that why I am telling these things. So, Reynolds number. It depends on several factors. This is density of fluid, this is velocity, and this is a characteristics length. I will come to this point within a minute. And this is the viscosity. In some literature, well, it was a bad animation. I was supposed to hide these things, but still it's there. So in some literature, you will find that Reynolds number is given by VL by S nu. This is known as kinematic viscosity. The kinematic viscosity means if you look at that, and then this is kinematic viscosity. Again, this is basically mu by rho. That is the viscosity by the density ratio. So it is not just simple mathematics. What is the physical expressions? The viscous force, you know, this is the Newtonian law of viscosity. If you, I will not get into those complicated part of non-Newtonian law. Newtonian law is which follows the equation of viscosity equation of Newton. That is the force equals to the viscosity and the strength. This is the equation. So basically, what does it tell? That is the force or the resistance of a matter against flow. And physically, it means that the force that has to be imposed on a substance, on a material, to keep it moving at a constant velocity. But what does this kinematic viscosity? The kinematic viscosity, if you play with the units, you will see that this is basically momentum. You can do it yourself. You play with the units. This is momentum. So kinematic viscosity means this is the force that will be applied for a substance to check which substance move faster. So all are moving, but some people will move faster than the others. And that is a measure of kinematic viscosity. And that's why in many geological situations and in mechanical engineering, where you have this oil through the, in cars and in many other places, and maybe you so need, so people are more interested about the flow properties, not on the fluid moving at a constant speed. So sometimes you need a material which for a given pressure moves faster, and some other materials move slower. Depending on your need, you will choose the material. So they use this kinematic viscosity. I'm sorry if I actually intrude your course in fluid mechanics, but these are little things. If I don't discuss, then I cannot really put things in perspective. So I am very sorry if I intrude the course of others, which I am not supposed to do. Okay, so this is the difference between the viscous force and the kinematic viscosity. Fine. Now, basically, if I want to understand it properly, this part is inertial force. Inertia, there's a property by virtue of which the matter wants to retain its state, whether it is static or whether it is in a moving state. Viscous force, that I have just discussed. Now, if we look at these things, you have rho. Its dimensional formula is mass per unit volume, velocity, length per time, characteristics length, unit of length, viscosity, that is pressure into time. Now tell me, if you play with these numbers, can you convert it to force? You do it yourself. It's trivially simple. With your knowledge, you can do it like this. If you play with this, you play with this and see if you can convert it into force. Because if you deal with the dimensional formula and rearrange, then it should give you the unit of force. Try whether you can do this. And then you try with the ratio. Then you can see whether you can translate these things to these things. So I will not get into the derivation. This is trivial mathematics. You can do this. But anyway, so you have inertial force, and that keeps the flowing water moving. And the viscous force, that is dragging, that reduces the velocity. So their ratio gives you the Reynolds number. Now, what is this characteristic? Let me calculate. Characteristic length is basically it gives the length of the system. This is more philosophical but extremely useful. That you have a system and you can think of its length, and that length is characteristic. This is not between the distance between 2 points. Well, it may or may not, but this is known as characteristics. Now, what is characteristics? Because the Reynolds number depend on this L value. The more the L value, Reynolds number will be more. So for a cylinder, just look at me. There is a flow like this, and you are putting a cylinder like this. Okay, the flow is coming and overcoming, is just climbing and then coming down and going like this. And this side is circular. So that is what you see. The characteristic length is its diameter, if this is a cylindrical body. If this is an airfoil, I don't know whether you know this airfoil, is basically is an object. If it moves, it gives an upward motion, that is thrust. Upward motion, like the blades of a fan or wings of a bird. If the flap, it goes upward. So this is known as airfoil. So if it makes an airfoil, the airfoil is, then basically its length is this. And this type of flow means external flow. That is actually the water moves past that substance. These two flows are known as external flows. It doesn't enter the material.